Hello, and thank you for joining us for our webinar with Hexagon. So today, Hexagon's powertrain engineering experts will share details of cutting-edge powertrain engineering and manufacturing approaches employed in recent years as the industry moves to electrification and the strategy implemented to ensure design intent is maintained throughout the manufacturing to electric vehicle. So today's agenda covers apologies. So our presenters today are, here's the agenda, sorry, excuse me. So we're looking at digitalization in manufacturing, ePowertrain design manufacturing challenges, data management, and digitalization in design. Our speakers today are Detlev Runkel, who's the Senior Business Management Development Manager for Automotive Powertrain Engineering Services team at Hexagon's Manufacturing Intelligence Division. Now, Detlev is responsible for global automotive e-mobility business consulting services and has more than 30 years of experience in the industry. He began his career as a project engineer for test facilities of engines and gearboxes. Our second presenter is Stuart Hughes. Stuart is Senior Technical Specialist for Gear and Manufacturing Powertrain Engineering Services at Hexagon's Manufacturing Intelligence Division. Stuart is a chartered engineer and member of the Institute of Mechanical Engineers with extensive experience in transmission manufacturing, quality control, product design and testing. And he leads a team of specialist engineers providing guidance and support for design and failure investigation. Now, before we begin the presentation, just a couple of little housekeeping things for our audience. We'd like to start with by encouraging you to send any questions you have for our panelists via the Q&A box in the corner, in the chat box. Just type them into the lower hand right side of your screen. If you also experience any technical issues during the session, just let us know in the Q&A box and our team here will endeavour to sort those out for you. So with that, I'm going to hand over to Detlev to begin with, to begin the presentation. Thanks very much.
Okay, good afternoon. Thank you for joining us. Yes, I'm going to be the one who's starting off with the presentation that we've prepared. So I will switch off the camera that you have the full picture and the full attention to the presentation. Now, today we are going to talk about the digitalization, but beforehand I'd like to give you a brief introduction of who we are and why are we presenting. So Stuart and I, we are presenting as Hexagon Applied Solutions, which is the engineering part of Hexagon Manufacturing Intelligence. We are covering the manufacturing side for Hexagon, which makes us also very prominent to hold this presentation today. The business areas that we are catering for in Hexagon Manufacturing Intelligence is, as you may imagine, the automotive, but also aerospace, electronics, energy, heavy equipment, rail, marine, and finally, life sciences. For these, we are developing novel workflows which are taking products from the concept right through production until they are delivered to the customer. What do we mean with this? So where are our core competencies? The Hexagon is coming from the capture of reality by having the right measurement equipment for manufacturing to ensure the quality. This is one arm of the business. So, for example, we can mention Leica and lights as the Hexagon measuring device providers. The second arm of Hexagon is dating back to the 1960s when they started with software, for example, MSC software, which is producing tools like Adams and Nastran. But also recently in 2020, Hexagon acquired a company called Romex, and this is where Stuart and I are coming from, for the simulation and the engineering of electrified powertrains. So we've got on one side the capturing of the reality with the measuring equipment. On the other side, we've got the design and the simulation tools, which enable us to design novel products. And then we've got in the Hexagon family as well technologies which enable us to move from automated production to autonomous production, meaning that we can do a much nicer workflow through the complete production plant and the development life cycle. All this is going to work because we are leveraging the data which are available to us from the measurement, from the design, and from the autonomy within the plant. We will talk about that in a minute, and I'll go a little bit further down. Briefly, when you ask what is Applied Solutions standing for, we are the link between the digital world and the real solutions, which means in the end we have shown in many projects that we use the right tools to come up with novel designs. And you will see in the moment that we are using quite a lot of pictures from electrified powertrains. This is very simple. It's a very nice template for us to use the pictures of electrified powertrains, because we have done many of them in recent years. And this is one of the key areas in industry where we see a lot of business happening. And they're all asking, how can we make workflows more efficient, and how can we get our industry or our production facility ready for Industry 4.0. So this is the link, and this is our justification for being in the game. The portfolio that we are doing is, in the moment, you've got design and engineering, and in the old days they were pretty much siloed, nothing to do with production and nothing to do with metrology and inspection. So traditionally, design and engineering is optimizing designs, is looking that things can be manufactured as designed. And the things that we saw in all these years is, yes, they have to aim to reduce the number of prototypes by doing a lot of stuff virtually upfront before they go into production or before they are being even tested. In the production side, we see that, yes, production aims to stay where the design is supposed to be, so maintain the design intent. Of course, they are trying to improve the efficiency of the processes, and by doing so, reduce the waste and the reworking efforts that have to be done if things go wrong. And also, they've got to make sure that at the end of the day, all the products leaving the production plant are delivered and are delivered on time. Now we have designed the part, then we have made the part. Now we've got to check that the part is still as designed. So we've got to capture the real world data by putting it through the measuring chain. We've got to check as well, is our process capable of delivering what we want it to do? And very important, it is the quality that comes out of the production line at the end. This is what we are doing today. And you see there is little traffic happening between these three. But if we are kicking off the digital transformation, all of a sudden these parts are talking to each other, communicating with each other much more than they used to do in the past. And the data flow is going to be quite accelerated, and the exchange of data between all three arms of the production is going to be increased. We are aiming to integrate the feedback and the improvement also to integrate it with the complete enterprise, and by having sufficient data available that we can apply artificial intelligence to make life for the engineers in the design and engineering, but also in production, easier, so that they are able to provide goods in top quality in very short time. This was to set the scene in a very broad and big picture, but now let's see what is happening actually down in the development process. First of all, let's have a quick look at the challenges which powertrain engineers, and again, I'm coming back to my ePowertrain, what are the challenges they are up to? So in the ePowertrain, the key questions are, number one is, of course, I have to deliver a very high power density, but to provide this, I've got to select the right architecture, which I can do up front in a virtual model. So to answer the questions, how do the parts integrate with each other, and will the other parts of the vehicle be fit for performance, cost, and weight targets? Once I've selected a very nice architecture, then I have to come up with durability. And those of you who have been in the ePowertrain development arena know quite well that the initial ePowertrains were failing for durability when the teeth were breaking off during coast down. And this is one of the questions that we have to address at first. Will all my parts survive the expected life cycle and achieve durability? The second wave then will be, is the noise and the shake of the vehicle being felt by the driver and the passengers? Is it a comfortable noise or is it an unpleasant noise? And again, we have seen many projects where we had to resolve some NVH issues where electric motors and gearboxes in combination were producing unpleasant noise to the passengers of an electric vehicle. And lastly, and this is one of the key questions in the moment, is number one, how far will my vehicle go with the energy from the battery? Is the efficiency. So can I improve the efficiency of the vehicle by having different technology in it? That's the challenge for the designers. But then somebody has to make it. So let's have a look at the manufacturing challenges. Efficiency, again, is here the key element. It is cost-driven, as we all expect, which means the man responsible for the plant has to find an answer to the question, how can I make the parts and the system in the most cost-efficient way? And immediately linked to this is, how can I make the parts and the systems in the shortest time? Of course, we shall not forget quality. So we've got to provide the highest quality at the lowest cost, which is acceptable. And in the recent years, of course, sustainability is one of the key elements that has to go with it, which means a plant which is maybe called a dirty plant is something that you can't run today. I'll be brave. So we've got to be sustainable, which means we need less material, less energy, less waste. And these are the key challenges to the people running the plant. Both of them have to come together. Again, looking back in the old traditional way, and very deliberately and on purpose, you see a very nice brick wall that we did put between the design world and the manufacturing world. And I say we did it on purpose to be a little bit provocative, to show better how we are going to address the issues that we are having today. So let's get started on the left. You've got the traditional CAE, traditional design, theoretical design. You're coming up with a nice drawing, which is being made in a 3D CAD program. Somehow the 3D CAD is to be transported into a 2D drawing to go to the manufacturing plant. Typically, somebody has to push some buttons to do it. The manufacturing documents out of the 2D drawing had to be made manual. So you had your process sheets, which had to be created for each machining operation, like milling, like turning, like heat treatment, whatever you have during the production. So this had to be done in paper form, and from paper form, you then had to transfer it into the machine. So somebody had to type something into a CNC machine to make the parts that it was supposed to do. Following this, the manufactured parts had to be tried out and checked that the processes were coming through, and you had to check that the quality is coming through, which means, okay, again, manual input into the measuring system, manual feedback from the measuring system to the machine to make sure that the parts are as you want them to be when you are coming out of the production. And at the end, you still have, again, your paper drawings and your standards against which you are checking that everything is correct and you are ticking the boxes. This chart you may have seen before, many times before, but we like it. And the nice thing about it is we can show here nicely on which screws do we want to turn to make the development much slicker and much more efficient. Again, in the early phases where you have broad targets, you need to have fast tools to do your digital development. In the later phases of the digital development, you can you get increasingly tighter targets, and you've got to optimize them. So that's the digital world. And then it goes out into physical world where the parts are being made. And while being made, you see a ramp up of the effort, which is supposed to fizzle out during the validation and production time. Occasionally, we have seen a double hump in the old days when during validations, product failures turned up and we had to rework and improve the product again. And this was costing time and money. Setting the scene with this, we are now going into the digital design phase, which is then going to be the prelude to what Stuart is going to talk about during the manufacturing side. So the digital thread that we are talking about is starting with the requirements capture, which means on the left-hand side, we'll start with requirements. So we see which risks are we taking, in which simulation environment are we working, what is the enterprise architecture that we've got to look at, and also how do we keep the quality and the certification. And when you look at it, you will see we have two double V's. One is the traditional V for the manufacturing in green at the bottom, and the other one is the V for the product virtual verification and the product validation in physical. So two V cycles combined to one. So with the requirements and historical data, you then start with the buzzword of MB, model-based system engineering. So here we are using model-based design and simulation, which is just like a gene pool intertwined. And we can follow in the product virtual verification how the design is being checked and tested during the design phase in a virtual world before it goes into the physical world being made. And the same thing we can do with the manufacturing. So we can try out up front that the tools that we have available and the processes are enabling us to produce the goods or the parts that we want to make in a nice and seamless way. So once we've got the physical system as a solution, we can then use the digital twins for the monitoring, the diagnostics and the prognostics. What is the product going to be? So we can monitor the quality that is coming out of the plant, but also we can diagnose why do we have any failures with our products, and we can also make prognosis to say how is a greater tolerancing affecting my final product. And via the digital twin, we can feed back these data into the product development or into the process development to manufacture it. So the aim is to close the loop. Now, this is a nice picture, but let's have a look, how does it work in reality? So during the powertrain design process, we'd like to show you the process from the first ideas right through to manufacturing. So starting off in the left, we've got some concept pictures where we are having some ideas that we put to paper. And with these ideas on paper, we are starting to feed some CAD models, some CAD images. During the development of the CAD, we are going to check the materials. So we are selecting the right materials. We are analyzing the structures that we are going to face. We run analysis for durability, for example. We run also analysis for the dynamics, and close to the dynamics is the acoustics behavior. We run efficiency, which is linking the computational fluid dynamics for coolant flow in a ePowertrain, but also linked to the CFD is also the thermal behavior of the whole system. And we can check the electromagnetic forces, we can see what multi-body dynamics we have. And with all that, our 3D CAD system is getting refined with every iteration. And we are going to have at the end a very nice and detailed design from which we are then able to deliver some data. These data, it's got to be made, designed for manufacture, as you may imagine. So we've got to do the digital manufacturing of the product up front. Say we are starting with a software model in Romex software. We do a virtual manufacture of a gear tooth. With this virtual manufactured gear tooth, we can do virtual measurement. And by doing this, feeding it back, the as manufactured data into the software, we can then test and validate the as manufactured product and improve our design in a closed loop. This does not only work for gears, but we can do it with other tools in the Hexagon portfolio, with sheet metal, where we are using Simufact or Cost Optimizer to work on sheet metal and check that the tools are all work, that the design is all fine. But not limited to this, we can also go for additive manufacturing, where Stuart is going to show us later on a nice example. But we are also addressing the impacts on additive manufacturing for the design process. Once we've got our virtual manufactured design, I indicated it already before that we can do a virtual test. And here in the example, we have bolted a little e-machine to a fixture and run it for acoustic NVH testing. And I can say that the results between simulation and measurements that we did were excellent. With this, we've got a virtually validated design, and out of this, we are then pushing it into the manufacturing. So we do the CAD to CAM transfer, we can check the cost, and we get the CAM data, which we are feeding then into the manufacturing machinery. Coming back to my initial picture, you will see some changes. In projects that we delivered, we saw that we were able to cut back the time and also cut down the cost for the development. Of course, we had to increase the digital development slightly because we were putting more effort into the digital bit. But it is compared to the savings that we have in the physical development quite significant. With this, I'd like to hand over to Stuart. Oops. So, Stuart, it's your turn, and I will push the button for you.
Thank you, Detlev. Hello, everybody. Good afternoon. I can't see the presentation, Detlev. Oh. Detlev, you made me the presenter, and I can't see the presentation.
I didn't make you a presenter.
It says you've been made the presenter. Sorry about this.
I can see the present. Well, of course I can see it.
Yeah, I can see it now. No,
okay,
yes, I can see. I can see it again now. Thank you.
Okay, sorry
about that. Okay, so this slide, connecting manufacturing, all the solutions on this slide all exist today. So you can see on this slide there are a number of different ways of digitizing manufacturing. So we've got something called paperless travelers, which is putting instructions and documentation on into a digital document pack, and that gives people the latest instructions and documents. It's an instant access to quality issues and bottlenecks as well. There's asset management, which is status of machines and real-time measured data. We have some virtual assembly, deviations between actual and manufactured geometries that you can look at on a 3D CAD screen. You can look at difference between actual assembly and virtual assembly. This mainly focuses on body shop assembly at the moment, but it's expected to extend that further. Connected worker gives instant event notification, faster decision making. Maintenance engineers have access to 3D models and drawings while on site or at the machine, so it's quite a good tool. Digital quality reporting is up-to-date data on quality data. It's visible to both manufacturing and design engineers, so that's an improvement on what we do today. Line walks basically trigger if something goes wrong. A driver for asset reliability, basically. We can use that information to focus on issues and corrective actions, any potential issues and corrective actions. We have execution and traceability, which records and reports exactly what's happening on the shop floor without the need for any paper. We move away from manual data mining and paper reports, and it basically embraces all digital operations. Utilization monitoring, reduced downtime, better planning and work scheduling, and AR for process optimization. We can scan QR codes, attach to assets, and display all the up-to-date information. Access to all documentation related to the operation and maintenance of all the assets, and it also gives the user the ability to view all the documentation videos without ever leaving the app. So it's quite an improvement on where we are today. Next slide, please, Detlev. Thank you. So for electric powertrain manufacturing, it will typically include all these processes from the left to the right. The arrows just represent the connection of the processes so that all the relevant data can be shared between the processes. Each of the individual processes use several existing tools to simulate real world. We can predict costing and plan manufacturing operations. It allows traceability of parts through the whole process. It has live work in process tracking, so we know where every part is in real time. Whether we choose a subtractive manufacturing process or a machining process or an additive process, there are tools that can simulate both. So we have toolpath simulation tools and additive manufacturing simulation tools for those particular, for things like powder bed fusion, direct energy deposition, metal binder jetting. Metrology, that's evolving quite rapidly. Software can collect data for import into design tools. We have instant comparison with 3D CAD models. We can create 3D images with scanning systems. And all these controls lead to less problems on assembly and reduce end-of-line testing. Next slide, please, Detlev. Some of the specific tools for these things look like this. So for production machining, we have for subtractive manufacturing, we have tool path simulation such as EdgeCam and Esprit. These optimize the process and tool path and check that the work holding doesn't interfere with the tool. For additive manufacturing, we have the optimized geometry from Apex to simulate the 3D printing using what we call Simufact additive, that's for metal, and Digimat AM for polymers. So we can do plastics and metals. We can check for distortion and cracking. When we do those simulation processes, with additive manufacture, there's an issue with distortion and cracks, and the simulation process helps to eliminate those issues. SPC is well established in manufacturing. It's been around since the early 80s, or even slightly before that. We now have some really good simulation tools that can analyze the data and help with seeing instantly what's going on in the manufacturing process. And metrology, we have some CMM machines, we have PMM machines, which are position measurement machines that use Quindos for gears and something called PCDMIS for dimensional measurement. We can transfer that data to the SPC software for instant feedback on quality, and we can transfer that to design analysis software to look at continuous improvement of the product for an existing product. And I've titled this Right Technology for Right Application because that's what we're talking about. We've got to choose the right technologies for each application. Sorry, next slide, Detlev, please. So I have two workflow examples that I wanted to show you. One is this first one is a wheel carrier using additive manufacture. We've used Apex generative design to explore the design space. Generative design uses an algorithm, and what that can do is it can you can put certain requirements into the software like weight and stress targets, and the software will search through all the different iterations of that, and it will create some appropriate solutions for that particular design. We can then pass that design to Simufact, which can look at the manufacturing of that part and if there's any issue with any stresses due to distortion and residual stresses in the part when it's been printed, so where it might crack or there might be excessive distortion. We can then take that simulated part and put it into the 3D printer and manufacture that part. Following the manufacture, we can measure it using CT scan, and the CT scan we can transfer that data into what we call volume graphics, and volume graphics can create a 3D model of that CT scan, which can give the dimensional information, and in addition to that, it can give the structural information, so things like any porosity in the part or any other defects within the structure in the part which a dimensional check won't give you. We can then pass that data back into the analysis, and we can analyze the part now with the structural information that we don't get when we do the original design, because original simulated design doesn't take account of porosity and such things in the structure of the metal. So we can use that within the analysis, and then I've called that continuous improvement. We can pass that back through if we want to, and reanalyze it for manufacture again, and remove some of that porosity and some of those areas of concern, and go through the loop again if the issue is bad enough. Next slide, please, Detlev. This one is a gear. It's subtractive manufacturing because we're removing metal. So again, we can design the part using Romax Designer in this case. We can pass that into a simulation program that will show us the the form of the gear flank, as in this case a gear grinding process, because that's quite a common process in electric vehicles. And then because of the way the modifications are put into the gear flank, we get a difference between the nominal design flank and the real manufactured flank. The kinematics of the machine caused a change in pressure angle and such things along the 3D flank, the topography of the flank that will contact the mating part. We can look at that simulated flank in the design, and we can look at the things like TE and tooth contact analysis, TCA, and we can modify the design if we need to for manufacturing. Again, we can then manufacture the part on the gear grinding machine and measure the part, and we can pass that measured data. We can look at the measured data. We can pass that measured data back into the analysis design program in 3D, so we can look at the actual flank of the measured part against what we designed and what we simulated, and we can, if we wish to, we can improve the design again. Next slide, please, Detlev. If we look at our graph again, if we make those types of improvements to our design process and our manufacturing process, we see further improvements in cost and time, and more efficiencies can be gained by making the processes digital. There are potentially lots of connections and lots of data, so it's important that we capture the data with the most useful information. And if problems do occur, there's traceability at the touch of a button, back to material, machine, cutting tool engaged, because we've connected everything together. More manufacturing options can be explored in a simulation environment, so we can design parts for a process, we can use the data to improve it. It's much quicker to do that. When we come to manufacture the prototype, the prototype part will be closer to right first time, because we've done a lot of the work in the simulation environment, not in the physical environment. We will use artificial intelligence, will get used. Artificial intelligence is the link really between physical world and measured data. It's important because we'll have large amounts of data from manufacturing processes in the future, and AI algorithms are needed to manage this amount of data. We can't manage this amount of data, and it's how the data is used that will determine whether it's successful. If we talk a bit more about that, we talk about design to engineering to manufacturing to production, assembly, and quality. We talk about capturing the reality from the physical world and then simulating that reality in this simulation environment and simulating the as-built part, and then applying that knowledge and feeding it back to operations to improve what we're doing. So it's all about continuous improvement and data-driven continuous improvement for predicting issues and preventing problems. Next slide, please, Detlev. For this to work, all these departments, design, engineering, manufacturing, and quality, that are involved, need to be connected. They're all in a loop, as you can see. For manufacturing, that would include the material planning, purchasing, maintenance, tool and cutter grinding. All the departments that are currently involved in manufacturing would need to be involved in this digital world as well. So we'd have to collect data from all those processes. Data-driven systems predict potential problems, we prevent waste. All data is visible in real time. We get instant feedback if we do that. And continuous improvements data-driven. If we predict issues, we prevent problems. So by predicting issues, we're preventing problems and making the most sustainable process. Next slide, please, Detlev. And if we talk about connecting people and processes across the life cycle, by creating all those solutions, we connect the people and the resources, we improve decision making, we create efficient processes, we use less material, we reduce waste and use less energy and reduce pollution. Basically, we create a sustainable process. Next slide, please, Detlev. So we're back to the original graphic that Detlev showed. In summary, transforming to a digital solution is central to our goal of creating a sustainable solution for ePowertrain design and manufacture. People describe it as the enabler in improving design and manufacturing processes, which is a good way of describing it. AI will be important because we have large amounts of data, and large amounts of data are better in an AI system that can crunch them and see trends, look at trends and look at and match trends to the physical world. They can be taught to do that. And we as people can't handle huge amounts of data like that and see those things in an AI system is better than that. But we'll always need engineers to create new ideas and to create the next revolution in whatever happens in the industrial world. Next slide, please, Detlev. And that's everything. Thank you very much for your attention.
That's a great presentation, Detlev, Stuart. And we're seeing a lot of this this sense of departments and the manufacturing, engineering, design side all being joined up more by these kind of systems, this kind of data. And I mean, it's a great presentation because you showed the scope of what's possible and what's being applied out there. And you're both, with all due respect, you're both industry veterans in this. So you,
the grey hair gives it away.
but I mean, this when we just before we get into the Q&A, this must represent a real transformation for manufacturing operations, especially now as we're moving into the electrification. Because Stuart, you're talking about gear grinding, which has been around for decades, obviously with transmissions. But before, that sort of quality control was very reliant on sort of set parameters of the material, on the weight of it, the type of steel, etc., all being used. And now the depth that you can go into in terms of analysis of the material, the performance, the durability of it, and even the NVH. I mean, one of our panelists, one of our audience commented on how interesting that is. And it's a really important part of obviously the EV side. But I was just curious to see how all of this is being adopted by. What's your take on it? What's the trend with your clients in the way that this is being adopted? Are they two things really? Are they embracing it as a big package as you presented there? Are they more interested in sort of bite-sized bits for various areas? And secondly, a question which has popped up a little bit with us is, with your clients, with the OEMs and the tier suppliers, how prepared are they in terms of their data management for these kind of systems? And do you have to lend quite a bit of support in implementing and integrating these systems? So the first question is kind of how is it being adopted? Is it in these big packages?
Stuart, do you want to answer this?
I can have a go. It's not. Over the last, we've seen an acceleration over the last 10 years, 15 years. There's an acceleration towards people using that first slide I showed about the individual packages. There's a lot of people buying individual packages, and so like the additive the AM one, for example. That's a more recent one. Maybe I shouldn't use that one, but as an example, they buy individual packages and put that in their process and see a benefit from that in that particular area, but they're like the siloed packages. It's not joined. There's no joined up. Industry 4 is about. I didn't want to use the word industry 4 because it's used too blandly. But industry 4 is about joining these things together and getting the full benefit of this system. The only way you get the full benefit of the system is by linking it all together. If we buy individual packages and silo them and say, oh, I'm going to improve my quality, I'm going to improve my gear cutting process or my turning process, it will do that. It'll do that, but it'll do it in isolation. You don't see the full benefit of the connectivity of it. If we connect it and we connect design with manufacturing properly, I know we've had CAD/CAM for the term CAD/CAM has probably been used for 25, 30 years, and we say it, but there is CAD/CAM and there is CAD/CAM, and CAD/CAM today will be, if we can do what we've just described, which is the connectivity between those systems and the simulations that we're have been developed and will continue to be developed and get even better, that will become a real reality. It'll become a reality that people haven't seen before. People maybe think that, oh, CAD/CAM, we've seen all this before, but you haven't seen it like this. You have not seen it like this. This is different. This time it is different. We've got computing power now. There is quite unbelievable compared with even 10 years ago. The computing power we are able to do this now. When I was in manufacturing 20 years ago, I moved into research and development from manufacturing. I spent 24 years in manufacturing, and I used to think about things that we're doing now. I used to think, why can't we do it like this? Why can't we do it like this? We had computers in the 1980s doing SPC in the manufacturing. Little Hewlett-Packard HP80 computers collecting data from taser gauging. But now, we thought we were being clever then, and we were, but it was all in isolation. It was all in pockets. There was nothing. The people joining it together were people. What we need to rely, if we're going to collect loads more, even more data, we were collecting 30-part samples then. If you're collecting 30,000 pieces of data from every operation, you've got tens of thousands of pieces of data. You will need an AI system to handle that, and you will need to have the connectivity, and you will need to benefit from that investment as well as a business. And it can be done, and it will give you a massive benefit in terms of waste and energy. And we talk about sustainability as well, and it's a word often used just blasé-ingly, really. But that is achievable. Using these systems, it's becoming more and more achievable. It's becoming real. It's becoming real. In the next 2 to 5 years, it will become very real. And people who don't adopt this will be the ones left behind.
And I can add to what Stuart is saying in very simple words. You were asking about the early adopters and what is happening out in the industry. Our experience is during the last 3 to 5 years, there were many of our customers asking us, is my business ready for Industry 4.0? Will I be on the winning side or will I be left behind? So we've done a couple of projects where we were looking into the processes and how to improve them. Yes, it is a big thing going through the industry, and the people who are out there and questioning themselves, are we ready for it? Our answer is, if you ask these questions, do something immediately.
Yeah.
Sorry to be that brave.
It's an interesting one because obviously the implementation of technology like this into what are pretty legacy processes and operations can be quite challenging. And interestingly, we've just had a question in from our audience asking a kind of similar thing, really. So the question is kind of, what are the pros and cons of implementing a digital transformation strategy? And in your experience, because obviously you're dealing with a range of clients, so in your experience, what are the most common reasons for failure in that? Where do you see the most challenging aspects for someone adopting this?
The problems when adopting this process is number one, to be aware, what are you doing? What are you improving? To have a clear target, and then to have the guts simply to do it. Failures, I don't think there are failures, because you are making a transformation from one process to the other. You may realize after a while that you may not have been brave enough to jump far enough. That's one thing, but that's a failure that can be corrected. So you can implement additional processes, additional tools into it. I haven't seen anything where we say, ooh, somebody bought the wrong tool. No, it's not a question about the tools, it's a question about the process that you are applying. And with this process, there is not that much you can do wrong. It's probably more a question, have I done all the things that I want to do? And again, you can do it in a staged approach, depending on budgets, depending on willingness to change. And the willingness to change is one of the elements.
It's an interesting response because it's
in a philosophical way, but I think it is describing quite nicely how it works.
Yeah, and it is interesting because it's sometimes challenging existing philosophies within a company, within a process. One of the one of the questions, I mean, I wanted to go back to this actually, right at the beginning. I mean, obviously, sorry, just going back to that point you were making, in your presentation, you described the criteria that you have to establish when you're moving forward with this. You know, it was kind of very key. You had a very clear sort of step process of deciding what you wanted to achieve at the beginning, deciding what those gated sort of stages were and how that went through. And that was interesting, like you saying, that first bit, understanding what you want to achieve with it, because obviously, I mean, a lot of data's out there as well. You've got an existing process, you're working to certain engineering parameters. It can be quite challenging. I wanted just to go back a little bit to right at the beginning. You were talking about design and manufacturing working close together, the brick wall slide, which seemed quite common, but I mean, we again, you know, we've done some interviews around design, engineering, manufacturing working closely together. Do you see this, and kind of do you see this being implemented in a positive, you know, in an actual kind of way, rather than kind of by the very nature of the fact the technology is there now that helps it? Do you actually see this being implemented as an actual strategy and policy within companies?
Okay, I think I can answer this. As Stuart was already pointing out, we see people who are implementing tools, but still working siloed. And one of the key elements to be successful is connecting all the individual departments, individual people that are working with it into a seamless and streamlined workflow out of their silos. And you will be surprised when you're talking to customers out there, how many are still thinking in silos. Maybe it is heritage, maybe it is age, but it's the way it is, and things don't change overnight. It's an evolution. They have to go through the steps. We see customers who have bought the tools but not fully rolled out, so it is taking time.
It will change the process. The problem is that the process will have to change as well, and a lot of businesses, maybe it's more, I think sometimes it's more difficult to change. It's easy to put a tool in, but to change the process is more difficult, because that means people have to change the way they do things, and that's the harder part, really. You can throw money at things and buy tools, but how do you make those work? And you make those, you can see that this system will change the way we work, completely change the way we work, and as long as we make improvements and we talk about a greener world, it's all, and sustainability is all about that. We need to move away from what we're doing. We need to be creative and move away from what we're doing. We need to make changes, otherwise nothing changes. We can't carry on doing what we're doing, in other words. And this is probably the most radical one of the most radical things that's probably happened, as people rightly say, in the last 50, 60 years, even since the CNC machines came in a big way, I guess. So yeah, processes have to change as well.
Just to confirm what Stuart is saying, and maybe let's go back to the old days when we were not that old as we are today. But in the old days, when I started my engineering career and you were developing a powertrain for a company, say Mercedes or Opel or VW or Porsche, whoever, typical development time was in the range of something like 7 years. And at that time, you had something like 50 or 60 odd prototypes available to play with. Some 15 years ago, the number of prototypes is down to 15, and development cycle is 3.5 years in Europe. If you talk to Asian customers, they'll cut it even further down. So you can't use your traditional processes. Very simple.
I would say big change. Speed to market is massively important now. It's a big deal. You'll probably be glad this is a question from our audience, less philosophical than some of mine, perhaps. So perhaps a little more direct, more relating to the sort of systems. Where are we? So this one is more probably application sort of specific. How do you make a decision on material choice impact on design, especially on applications that are failing within existing standard materials. So I mean, going back to the idea of using existing parameters, engineering specs, etc. How do you kind of make a decision on material choices? I mean, from utilizing what we've discussed or you've discussed today.
I think material choice, number one, of course, let's stick with the things where we are coming from, rotating machinery, gears. So if your standard gear material doesn't help you, you may want to go to a higher quality, i.e. more expensive steel, for example. That's one solution. The choice is, again, engineering practice. You see it fails, you identify why did it fail, and then you have to find a solution. That's I think a normal process. So if your material isn't fit for the job, you've got to find a better material. Very simple answer. It sounds simple, but again, you've got to use engineering judgment, and this is then again playing with Stuart when he's saying we always will need engineers who make decisions and make good decisions because they know what they are doing. So with all these wonderful tools, we won't make engineers obsolete. We always will need them, and they have to make a decision.
The biggest change in materials will be, I think the CT scan and the graphics is really good, because being able to actually use the structural housing within analysis is completely new. That is completely new, and
Yes.
the volume graphics and normally when you design a housing, you usually look at the high stressed areas. You don't bother too much about the other areas really, but often there's porosity all over a casting for various reasons. There's defects all around the housing for various reasons. So if you can look at that back in the analysis software in terms of, in addition to stress, NVH, for example, your NVH would be completely different if you start to put air rolls out, make it into an aero bar. You start to be able to look at aspects of a design that you never even thought of. Well, you didn't think of looking at them because you couldn't. You thought about it as an engineer, but you never had a tool that allowed you to do that. We're now developing tools that actually let you do that, and I'm sure with forgings, for example, going forward, the forging, we can simulate the forging process. We have a tool that can simulate the forging process, and I'm sure that moving forward, there will be people who will who are far more knowledgeable about forging than I am, and I know a little bit. I know about forging, but I'm not like the people who do it every day. That they will take that tool and they will use those tools very advantageously to make their forgings much better than they are today. So you will start to see improvements because of these tools, really.
It's interesting, like you're saying there, the tools are supporting engineers, not making decisions for them. Yeah. But obviously, as you say, it gives you that visibility now around a design, a particular thing. And as you say, because the design is changing from what, as an engineer, you might have thought this is the correct design for this. But as you say, with the sort of EV side NVH, those parameters, the requirements are changing, and so it just gives you that visibility. We've got just about time for one more quick question here, and I think this goes back to your presentation, because I noticed this probably would be quite a big sort of area of interest for our audience. Is why do you need this for the EV powertrain as opposed to other parts of the vehicle? Why is this kind of so key? And I think we know kind of, you alluded to some of the answers in this, but if you can just give us a bit of, obviously it's probably a big thing you're seeing now in that respect. So we're talking about automotive manufacturers been building petrol and diesel cars for decades, now dealing with electric powertrains. So how is this relevant to that or needed?
Say we were using the ePowertrain as a template because we are working since years on electrified powertrains, so we have all these wonderful nice pictures. Of course, the processes that we are showing are applicable to any other product, to any other process. So for us, in the process world, we could apply it to making sheet metal for the bonnet. We could apply it to any other thing. The process is the key element here. So it is not bound to ePowertrain. But the other thing we can say, ePowertrain is the theme of the month that everybody is working on. And the ePowertrain producers have to cut costs so that people can afford electrified cars to save the environment, at least in some way. So there is quite a heavy drive in this direction from the industry. But as I say, it is applicable to any other product. The process is the key element here, how you do it.
There are different challenges in EV as well. If you compare EV to internal combustion engine, it's completely different. And we've seen that even when you apply the known qualities to EV systems that you apply to even better than internal combustion systems, you still see issues like NVH issues, and then people then don't know why they have a problem, that they don't then they come to us and say, can you explain to me why I have a problem, because everything is perfect but I still have a problem. Yes, so we're seeing that with some serious OEMs, and it needs a lot. We're shifting the thinking away from. We can't start sitting here talking about what we're developing, but we are developing things to move away from what we do today.
Right. Well, thank you both, Dale, Stuart. Great insights. Thanks very much for your time and your experience and insights into what's going on out there and this sort of technology, because I say it's fascinating stuff, and as you say, a changing industry and a big change in the way that processes are being approached. So with that, I'll be bringing this session to a close. We'd just like to say thanks to our presenters. As always, the webinar is uploaded to the AMS website and is accessible in the future for your colleagues who may have been unable to join us, or if you want to listen to it again. And you can access this and all the previous webinars via the Voice of the Industry link at the website. So thanks again for joining us today, and we hope you'll join us for our next webinar. So with that, thanks very much and goodbye.
Thank you.